All right. Good morning, everyone, and thank you so much for being here. So, I'd like to just introduce myself. My name is Varun Palahalli. I'm a technical specialist. I work for an organization by the name of Hexagon, and I too am a drone enthusiast, just like all of you fellow participants who are here today. And I did spend a lot of my years in college as well as high school. Um, Getting into building fixed wing drones predominantly. And then also now I directly work with drone organizations into supporting them and helping them use simulation to help better improve their design and also have their designs certified. So today I'd like to just share my screen, and for now I'll just stop my video and I'll turn it on again when I'm speaking to you during the question and answer session and things like that. So with that, I'd like to just share my screen and then let me get started with that. So please let me know if my screen is visible.
Yes, sir, we can see.
Yeah, thank you, Aisha. Yeah. So today I'm going to be talking about a small aspect of what we can do with simulation, sort of an introductory session. We're going to be looking at the linear static analysis of a multi-rotor unmanned vehicle. So this series is specifically for the benefit of the students who are going to be participating in SAE AeroTHON. And as you're all aware, AeroTHON is a very exciting opportunity to be able to get your drones, build them, have them validated by the technical committee, and then prove their capabilities in a live and hands-on platform. So it directly adds a benefit as to hands-on engineering, as well as gives you an opportunity to actually go ahead and apply these skills and even look for how you can make a living out of this. So as an organization, Hexagon is into manufacturing intelligence. So the division that I represent is known as design and engineering. So this design and engineering division is what specially deals with simulation of all forms of physics. So all the way from structural to thermal to CFD to multi-physics in forms of co-simulation, manufacturing simulation, additive manufacturing, and so on and so forth. So not getting too much into depth, I'd like to first start off this presentation as to what is our agenda, what are we going to do, and then I have some live demo sessions for you. And at the end of this, I'm also going to share how we can actually get started on this as a student, and students can go ahead, download this tool as well, and then start using it for your own multi-rotors for SAE Aerothon or beyond that as well. And it's not only limited to multi-rotors, but for the sake of SAE Aerothon, I'm going to be presenting something that's very applicable to our our colleagues here today. So with that, I'd like to begin. And a brief agenda is that I'm going to cover why is finite element analysis even necessary for a UAV. We can always build it without FEA also. And what is FEA as a practical overview? Next, we're going to see what Apex is and how it works and how it's going to benefit us in order to do this, how it eases our analysis process. And then we're going to take a look at the live demo. I'm going to share some links to you where you can get started. You can actually go ahead, register, download the tool as well, and use it hands-on. And then we can have some discussions from your end, and then maybe have a conclusive note from both you as well as our organizers at SAE. So with that, once again, welcome to this discussion. Thank you for making time on a weekend, and I hope you get some benefit out of this. And with that, let's begin. So I'm going to be talking about what is finite element analysis and why do you even need to use it. So I believe most of you are engineering students and you would be aware of what finite element analysis is as a theoretical formulation. I'm not going to go too much into depth into the equations of it because that's not the objective of today's presentation. What I am going to do is tell you where and how this is applicable and how we are going to use it for our benefits. So normally in any domain of engineering analysis, be it any kind of, could be a computers, could be mechanical, could be aerospace, could be civil structures, all of it. Whatever you design, it is normally an engineer's duty to test this, to validate this. Now, many a times, especially in the aerospace domain, when you're dealing with UAVs, when you're dealing with actual real aircrafts as well, it is a very expensive and time-consuming process to individually test these structures, each one at a time for every single configuration. So in many a times, you would want to actually develop a system or a UAV platform with a particular design in your mind, and you want to evaluate this before you even build it. You want to see, is this good enough to be even built or not? Is it going to be wasting your time or not? So how do we evaluate this? We start with something known as engineering analysis. Under engineering analysis, normally we have two methods. One that you're already familiar with, which is known as the classical method. So I believe all of you would have done some form of strength of materials, mechanics of materials, things like that, where you would have your shear force diagrams, bending moment diagrams. You'd investigate simple shells and some columns and things like that. So many of the classical methods come under what you can solve by using something known as a closed form equation. That is when you have a solution for your partial differential equation. So be it for a beam equation or a bar, any of your partial differential equations which have the necessary initial conditions and the boundary conditions that can be solved is known as an exact solution or a closed form solution. Now, you'll also be familiar that many a times you may not have a closed form solution. You may have an over-constrained structure. You may have the number of equations not matching the number of unknowns. You may have conditions where you simply cannot use a condition to satisfy your closed form solution. For example, you can see the Navier-Stokes equation when you're dealing with CFD. It lacks a closed form solution simply because it is inherently mathematically very complex. So you begin to utilize things such as approximate solutions like your Rayleigh-Ritz method, Galerkin method, energy approximations, things like that. Now, all of these can be scaled for simple structures. So you can see on your right top corner, it's something that you're all very familiar with, a stepped bar. You can easily solve this stepped bar by using closed form solution by a hand calculation. But what do you do when it starts to become very, very complex? Like, for example, one of the examples is like a quadcopter or a multi-rotor UAV platform. So this is where you begin to utilize what are known as numerical methods. To simply put, how a numerical method works in the most crudest way is that I'm sure you're all familiar with things like a Taylor series expansion, where instead of actually evaluating, you're going to use a numerical approach to get an approximate answer. However, that approximation based on the degree of the unknowns or the degree of the equation that you're considering, you are able to go ahead and sort of approximate it to an applicable, necessary, and sufficient answer. That is where engineering comes into it entirely. So we are going to be looking at numerical methods, particularly that of finite element analysis. You do have what is finite difference and boundary element also. But this class or this session is not particularly to deal with the theoretical aspects behind this. So we're going to get into some of the practical aspects of it. I'm sure you're already familiar with what is the finite element analysis. And to simply put it into words, we are able to see that you take any given structure and you discretize it with a number of known parameters which are behaving as elements. So you perform a spatial discretization. And this spatial discretization is what is going to be defining. So each element has a shape function which can be derived, and we know the shape function's behavior, so we can formulate each element to behave like a spring. So you have a stiffness matrix and a mass matrix, and for the applied loads and boundary conditions, you're able to evaluate the behavior. Now we simply sum up the behavior of all of these. We create what is known as a global stiffness matrix, and then we can solve the behavior of this structure quite easily. So in a simple way of looking at it, if you are asked to draw a circle without using any curves, you can approximately represent a circle with sufficient number of straight lines, provided your straight lines are small and you have many of them. you're utilizing a similar principle. And with the advent of digital computation, it is going to help you in order to analyze this using a computer program. You're basically going to compile this and ask the computer to solve this matrix equation in order to get your unknowns, which are your stresses and displacements. So you can see here that popularly you have three kinds of elements. You have the bar element, you have the beam element, you have all of these which are called the 1D elements. This come under the category of 1D, where you have long, slender bodies defined. Next come your thin-walled structures like aerospace structures. These are known as your shell elements. And these are for your solid bodies, which are known as solid elements or 3D elements. So these elements, you have many categories in that. I'm not going to get into the theoretical aspects of it, but you can always go ahead and refer to that. And we'll be seeing how we're going to be utilizing these. So what is the overall process that you're going to use as a practical overview of finite element analysis? What is the workflow? You go ahead and you take a continuous structure, which would be your CAD model, and then you mesh these in order to discretize these, and then you derive the corresponding element stiffness and matrix properties. These are all obtained automatically in your solver, something like Apex. And then you go ahead, assemble these, apply the loads, apply the boundary conditions, solve this, and then you need to compute the stresses, strains, and displacement from the result. This is a major objective that we're going to be doing. So what is MSC Apex and where does this give us a benefit in order to perform the above said requirements for finite element analysis? So when we get started, we want to use a platform and we want to apply the principles of FEA to do that. But what are some of the challenges that we see? Our CAD geometry may or may not be suitable for the analysis. Geometry may be prone for error. It may take a long time to clean up. And we would have design challenges where we need to remesh and we need to change some properties in that you may want to you look at the result and you say, okay, I want to reduce the length of this, I want to increase the thickness of this, so on and so forth. So sometimes you may not want to go back into a CAD environment and do that. Next, you may want to extract something called a mid-surface. I will come to this and then explain what is a mid-surface extraction. And normally, the way the solver interacts is that it will have a computer code, most popularly Fortran, like what you're looking at in this case, to communicate in the background and then solve your equations. But creating these manually take a lot of time. So you want to have a robust user interface to perform this. And also, as a student, you don't want to have any kind of a long lead time for training. All of you want to get started and you want to have like some hands-on approach. It needs to have some ease of use and so on and so forth. And maybe in the future, you may also want automation and things like that. So to answer all of this, you have a solution by the name of MSC Apex. So what is Apex? Apex, very simply put, is a integrated CAD, mesh, and solver environment, wherein you can manipulate the CAD, clean it up, you can make any changes, you can mesh this, and you don't need to remesh. You can, as you can see in these videos, if you make any changes in the geometry, the mesh will automatically conform to it, and you'll be able to regenerate the mesh and then perform the analysis. You also have the ability of extracting a mid-surface. Mid-surface is basically you want to represent a 3D solid structure as a 2D shell element. That is also something that's possible. And you can do some scripting in Apex. Very important for students is that you would want to have some pop-up guides and tutorials. All of that are inbuilt within Apex itself. Any tool that you need help with, you can do it. And you do not need to exit Apex to perform any kind of linear structural analysis. So all of your part level, assembly level can be done within Apex itself. So it works as a pre-processor, solver, and a post-processor all in one platform. And everything is sort of an interface which is graphical and user-friendly. So here you can see some of the geometry options that you can do: sketching, repair, revolve, sweep, extrude. So I'm sure most of you are familiar with CAD operations also. This platform gives you the ability of manipulating your CAD, cleaning up your CAD geometry, making small sketch changes, making any kind of defeaturing, so on and so forth. All of this is integrated. It is click-based, and you will have color coding as well. So it allows you to communicate with the tool in a sophisticated manner. Next, when we talk about mid-surfacing, this is something that you can explore in the future as well. This is a approach of converting a solid geometry, especially if you have like sheet stringer configuration, if you have any kind of composite parts. Normally, they're all represented as shell elements. So if you have a solid geometry in your CAD, you can extract a mid-surface quite easily, clean it up, and then automatically assign the thickness and offsets that are required for it. And the process of doing that is semi-automated in Apex. You're able to identify the pairs using incremental mid-surfacing, edit these corresponding pairs, merge them, choose the type of offset, extract the mid-surface, and then mesh it as well as assign the thickness. So you can see here, this is a solid geometry that you have extracted a 2D surface for that, and then you've meshed it and assigned the thickness for it. So such capabilities are also present. For those of you who like to use composites in your UAVs, most popularly these days, many UAVs are using composites for their specific stiffness and weight and strength as well. So in certain applications where you do need an orthotropic material application, Apex is fully capable of doing that for both 2D as well as 3D. And especially when it comes to 2D, you can create multiple zones and multiple layerings also, something that you can explore. And when it comes to meshing, you have the ability for solid mesh. You can also create hexahedral meshes, which are going to be mapped in nature. You also have an option which is known as a feature-based mesh. Feature-based mesh is basically you want to have any kind of refinement around the hole. You want to have any kind of refinement in a specific region like a fillet, so on and so forth, sensitive to a feature that can be done. Next, you have what is known as generative mesh as geometry. I will come back to this. This is one benefit where if somebody gives you a mesh file, you may have multiple teams working together. Somebody shares you just a Nastran input file or a BDF format. You can create CAD out of that, and you can also manipulate that existing mesh in order to refine and then utilize that. You also have some keen approaches here, especially when it comes to manipulating the mesh manually. So you can move nodes, you can align nodes without remeshing. It will actively regenerate the mesh according to your need. So it's quite user-friendly that way. And you also have the option of merging nodes in case you have a crack in your mesh and so on and so forth. So when it comes to assembly level, we will see that today contacts become essential. You want to create contacts which cause dissimilar mesh regions to be attached to each other. So it can be done quite easily in Apex. You simply need to select the type of contact. In most cases for linear analysis, we'll be choosing a permanent glued contact. So you can go ahead, select the regions you want to specify, simply drag a box. You also have an option of choosing manually, and it allows you to basically create contacts. So we will be seeing that. And this is exactly what I was talking about for the integrated CAE workflow where you're getting mesh to CAD. So if you have a mesh file, this is on your left-hand side, this is what a Nastran input file looks like. And you have the option of simply importing this into Apex. And you can see here, I have actually created a bracket out of the existing mesh, and you can export this bracket to a neutral CAD format like STEP, IGIS, Parasolid, STL, whatever like your choice. So you can create a mesh, and you can also import a mesh and generate CAD out of that mesh. So like I mentioned, you don't need to exit this platform in order to perform any linear analysis. So be it linear static, what we're going to take a look at, linear buckling for any kind of instability, frequency response, as well as normal modes. This comes under dynamics. So if you have any kind of normal modes analysis, you want to do a modal analysis of this for those who are familiar with vibration, it is also something that is possible. And you can also do frequency response. That is, what is the effect of a applied frequency on your structure? How is it going to react to that? That can also be done well within Apex itself. So what benefit does it give you? You have real-time analysis capabilities. You can modify your model, reanalyze it. And it also gives you a step-by-step approach to perform this. In addition to this, for those who would like to explore this perhaps in the future, you also have plenty of customizations available where you can write user-defined functions in the form of macros. These macros can be recorded. It's all in Python, so it's quite easy for those who are familiar with Python. You can go ahead, make the modification of the macro. You can add points to that. You can add customization tools. You can create your own tool. You can create custom processes also if you have any kind of repetitive approaches with that. So with that, let's begin with the live demo. So I hope all of you are excited to see the live demo, and I'm going to be presenting this live demo. So for those who are gamer fans in the student community, I'm going to do what is popularly known as a speed run of this approach. So we're going to go ahead and get started. I'm going to have this in full screen, and I will be giving you the step-by-step discussion as to how we're going to be performing this analysis in MSC Apex. And then after that, we will definitely have a question and answer session in terms of what we did, how we did that, and if you have any other kind of questions regarding this. So with that, let me get started, and let me just play this and then move to a full screen mode approach. Okay. So this is the kind of environment that you would have when you open Apex. So I'm going to go ahead, import this. You can see that Apex supports all of your neutral CAD formats as well as specific CAD formats. So you can have like Parasolid, you can have like IGIS, so on and so forth. You can also have CATIA part, SolidWorks part, Creo part, NX, so on and so forth. So here I have imported an IGIS file. You can see all of the bodies are under one part. So the left-hand side toggle column gives you a interface which is CAD-like. I'm just creating individual parts and adding the bodies to those corresponding parts, just so that I can define the toggling, hide and show, and so on and so forth. So you can see this is a quadcopter model that I have taken. It's a standard approach. You have your engine electronic speed controllers, you have your brushless outrunner motors, you have your propellers, and I'm just moving each of these to individual parts. That's all I'm going to do initially. Just going to put them. So you can see now these come under ESC. I have added them to this. And then correspondingly, you can see there are individual components which are going to be added. This one, I'm going to name it as props for the propellers. Going to add all of these propellers to that. You'll soon see why this is of a benefit, because I can hide and show individual parts. And I'm basically going to remove these fasteners because I'm going to use a contact constraint. I don't wish to model these fasteners in this model. So I'm going to reduce this. So this process is known as defeaturing, where I'm doing a geometry cleanup and removing components which are not essential for this process. So what I'm going to say is that in this analysis, I'm not investigating the structural capability of fasteners. However, I am investigating the structural capability of my design as an airframe. That is my keen interest. So you can see here, my fasteners are now removed. I have my motors. I have my propeller mounts on top of the motors, which is basically the shaft. And I'm going to do a Boolean operation. So you have full capability of Boolean add, subtract, Boolean intersect. All of these capabilities are already there. So I have Boolean this into one single body, one single assembly rather, and then bring it into this, add it into my part, and then give it a name as
हो गया था
motor.
आके डाल भी दिया खाली है जाना है तो तुरंत तुरंत चले गए
Yeah, Aisha, requesting you to mute the participants, please. Thank you. So I'm going to go ahead and hide these fasteners again, and you can see there are some electrical components which are not essential for my structural capabilities. So I've gone ahead and hidden those as well. And what I am going to do is I'm going to name this assembly as the central control board assembly, because I have a mount, and then I would have my flight controller coming on top of it. So you may have a generic flight controller, or you may have something like a Pixhawk or something like that. I'm going to also model that. We'll see how I'm going to do that. So what you can see now is that I'm basically left with the airframe itself. the structural frame, which is very important to me in terms of the design. Most of the other components are bought out, but this frame is normally designed by me as an engineer. So when it comes to complex structures, you can see that I can do a geometry cleanup. I can clean the topology. I can clean the edges, all of that. And then I also have what is known as defeaturing. Defeaturing can be done based on the faces and also the features. So you can see I'm going to be defeaturing this by selecting unwanted faces and then eliminating that aspect itself. So whatever you see as a cable sleeve and things like that, which are insignificant for this analysis, I'm going to eliminate this. So you can see this, and also I can eliminate the fillets that are given there because I simply need the block structure for this. And in fact, I'm not even going to utilize this for my analysis because I will soon show you what the benefit for this is. So you can see here each of these steps quite easily simply by clicking. You can also see how we can eliminate these by selected feature. I can select the holes and then remove them. I can select the fillets, remove them. And similarly, you can see for this one also, I'm selecting the holes, eliminating them, fillets, eliminating them by the middle mouse button. And simply going to be choosing these external, whatever sleeve components that were remaining and eliminating them such that I have blocks which would represent the mass properties which I'm going to apply to this. So you'll soon see where this becomes benefit. All right, so now I'm going to go ahead and then you can see I'm just saving this file over here just so that I can access this later on as well. And upon saving that, I can do a hide and show. Here's a show all, and you'll be able to see that my speed controllers are shown as blocks. And I can partition these structures as well by utilizing a reference solid because I'm going to be connecting what is known as a lump mass approach. I'm representing these non-structural masses, that is, whatever these components which are going to not participate in the load bearing capability of my airframe. They're going to be represented as structural masses in the form of points. So they're not going to take any kind of density. They're not going to take any kind of stiffness. But what they are going to be representing is a block mass that's going to behave over there. So we will soon see how I'm going to do that. So firstly, I partition these regions such that I can mesh this structure, and I can also go ahead and assign the mass for those structures as well. So next, I go ahead and then I take a look at the geometry cleanup operation. And here I can clean the entire structure as well. And before that, there are some small sort of connectors for these PCBs. You can see whatever is on these PCBs. I'm just defeaturing these again. So it's all click-based defeaturing. You can simply click and then have that entire component eliminated. Similarly for this one as well. So this would be where your maybe your power connector or could be like a USB link and things like that. So just going to simply eliminate that. And now I have just the base board that is present. So the next thing I can think about looking at is basically coloring this. So for any kind of operation, I can use an auto color or I can manually change the color also so that I can have some distinguishing. And then I can clean up this entire geometry again, which makes it meshable. And any kind of specific cleanup that needs to be done can be done. You can see whatever is partitioned will not be clean. So any cleanup that needs to be done, you have to do it before partitioning these structures. And we are able to quite easily do this in the form of a click-based approach. You don't need to specify any special characteristics for this. So once again, I'm also going to split this top surface. You can see here whatever is there mounted. So I'm going to split it such that I can assign a mass for the battery. I'm not going to create the battery as a structure. You can also go ahead and specify the battery as a structure if you have the material characteristics and the properties of it. I'm going to assign the battery as a mass body. I'm not going to assign it as a stiffness body. So it's a more conservative approach is what I'm going to say. So now you can see here what are the kind of meshing approaches. I'm going to use the solid mesh approach. And you can see here, that's it. You just select the mesh size and you click on the body of your choice and you're able to mesh it. So now you have the four arms which are meshed, and then you have the landing gear pegs, the mounts, whatever you do, the skids you may call it if you wish. And next, I'm going to hide the battery and then mesh the top surface, which is going to be the top. And you can see that this is actually conforming to the structure and giving you refinement around your features. And you have the ability of actively looking at the color also. So if you look at the element quality, you're able to look at the element quality according to a preset aerospace standard. You may also change the quality according to your choice. And here, what I'm going to do is I'm doing a local refinement. I'm basically refining these regions by using a 2D surface mesh. And you can see, okay, even with 2.5, that is half of that, it is still giving me bad elements over there. So I can delete the meshes. Apex also has undo operation, so you can undo it as many times as you wish. And now I'm going to use a 1 mm refinement over there. And then I meshed that. So you can see rest of the structure is still 5 mm, but only in those regions it's 1 mm. And now you have very good quality over there, very few bad elements and so on and so forth. So you can also use like a node move to like move specific nodes if you wish. And I'm just deleting that 2D elements that I created because I don't wish to do that anymore. So similarly here, first I assign a 2D element and then I use that to map out the 3D elements. So there are multiple ways of doing it. This is not the only approach to do that. And like I mentioned, you can go ahead and move nodes manually. So you can see that just got cleaned up. You can move this accordingly to see what it's going to be there. You have another one that's cleaned up, and then you have more refinement that's possible. So very few bad elements. That's an invalid element. So I undo that very quickly. And as long as you don't have any invalid elements, your analysis is capable of running. So it will automatically give you warnings if you do have invalid elements. It will not allow you to perform the analysis. So now I'm going to go ahead and mesh these regions as well, which are going to be my controller board mount, and then the spacers for the controller board mount as well. So you do have the seeding approach also, where you can seed an edge and then choose how many nodes you want across that edge and so on and so forth. You also have, this is the global mesh refinement approach. You can change the mesh quality for global mesh. And also what you will be able to see is that you can refine individual sides of this using a surface mesh, which will basically give you the opportunity of controlling the face like you saw earlier. So right now I'm refining only the faces. And you can see here by refining these faces, I can go ahead and then mesh the solid. So I'm going to change back to a solid mesh and then use a larger mesh. And then you'll see that, yes, it is in fact conforming to this face mesh that you initially defined. So it gives you an option of doing multiple kinds of refinement. And since I don't want any kind of 2D mesh right now, I have the ability of going ahead and cleaning this up. So you can see that it's green now, and you have the option of meshing this even in a hexahedral approach. So if you're utilizing the hexahedral elements, you'll be able to see these are basically like your brick elements, and you do have the option of splitting that and using this sort of a map method as well. But for the reason of conforming of geometry, you can see that during the curvature, you're not having appropriate quality. So I'm going to go ahead and then remesh this using the tetrahedral elements itself. Now, if you have any questions on what elements type are there and things like that, we can definitely approach this after this demonstration. I'll be more than happy to help you. So wherever it's yellow, it's saying that because of the mesh conformity, it's having some trouble recognizing the mesh simply because it is not possible to be meshed because there was some variation in the inputs that we had given. And now once we seed that appropriately, we can see that it is completely hex meshable again. So clearly this quality was struggling in terms of the hex mesh. So I'm going to delete this and go ahead and just use hex mesh for the spacers because they are well conforming cylinders. And then for the upper and lower boards for the mount, I'm going to go ahead and utilize the same approach that we've done before. So I first mesh the surface so that it will conform to that. And next, I go ahead and I mesh the solid. So choose the solid mesh, and then you get a beautifully conforming mesh in terms of tetrahedral elements, and the quality is superior. So pretty much we've been able to mesh the entire structure, so we can see what the entire structure looks like. So whatever is going to be flexible or participating in the analysis, that is something that you can mesh and utilize. So I am now going to go ahead and probe what is known as the mass properties of the solid. So I'm not assigned any material, but this tool gives me the CG of this part. So I'm able to recognize the CG of this part. So using the CG of this part, I can create a node there. So like I mentioned, I'm going to be creating a non-structural mass over here. So maybe what I'm going to do is, since this is a little critical, I'm just going to reduce the playback speed a little bit. Right, and then I'm going to continue playing this. So here you can see that I'm creating specific nodes at the CG location of each of these non-structural masses that I wish to assign. So these are all going to be lump mass, they're concentrated mass bodies. So you can see here that the CG of that entire mass is represented as a point over there. So utilizing this, I have what is known as a discrete tie. This is known as a multi-point constraint. So I'm going to utilize this multi-point constraint in order to assign what are my independent and dependent nodes by using this link. So this is something known as an RBE connector. So by using an RBE connector, I can assign the mass properties at that one single node and have that distributed on the entire other nodes that it's connected to. So like I mentioned, you have tutorials and you have lots of videos for everything that you'd like to study. All you have to do is go to the help window on your top right corner and then simply search what you'd like to see over there. And you also have exclusive documentation where you can see the steps, you can see how to do that, and you can see demonstration videos also. How do you create these kind of discrete ties and so on? Not only limited to discrete ties, you can do that for any thing that you'd like to look for. How do you do mass assignment, material assignment, so on and so forth. Next, I choose what is known as a point mass. So in this point mass, you can see that I have the ability of defining the mass moment of inertia as well as the mass of the body itself. For this example, I'm simply applying the mass, but should you be utilizing any kind of dynamic analysis or even going to utilize the analysis where you're trying to do any kind of matching to a particular condition, so on and so forth, it is always recommended that you would put in the mass moment of inertia of your structure as well. So I go ahead and I select that node in order to place that mass. So you can see that little anvil that's come over there, kind of like a kettlebell rather, not an anvil. And that kettlebell basically represents the mass over there. So the mass for this is obtained from a data sheet. You would have the manufacturer defining how heavy a particular ESC is going to be like. So go ahead, take a look at that, and then you can apply that. So similarly for the other ESCs also, I'm investigating that. I've made a small note in the notepad as to what are the CG points, and I'm going to assign the CG points according to that. So it's probed by using that mass properties tool. And then I create one node. So I just create a manual node at each of these points in order to have that single node to create the tie. So I'm going to hide this and then simply create a discrete tie over here. I'm putting it into the same part group as the ESC, hide everything else. And then very simply go and once again perform discrete tie, choose the independent and choose the dependent. So you can see here, there's one node that is going to be representing, you'll see one small white node over there. Yeah, it's in fact sort of grayish blue. Select that, and that is where once again you have all of your degrees of freedom and your choices for that. And you can go ahead and apply the mass and mass moment of inertia properties of your mass, whatever you're going to represent as a concentrated mass. So here, once again, this is going to be that of a ESC. So same thing I'm going to do for the other two also. So just going to go ahead once again into my query tools, go to mass properties, select the body, And then I've made a note of this already. And whatever I've made a note of, I'm going to create a node at that same CG location. So what's the major benefit of this is that we don't need to go and mesh things that are insignificant in our analysis because these are bought out items. I don't want to investigate the stiffness of an ESC component. It's basically like some sort of a PCB with some regulators on that. And then I also have a lot of cabling. So it's irrelevant to me in terms of the stiffness contribution. What it does do is it gives us a mass. It's a mass that's applied on that. So I want to represent it as a mass. So I can do that. I'm representing as a mass. And of course, it is slightly conservative. There may be a minimal amount of stiffness improvement when we use some sort of a tie or something like that, but absolutely not significant for my airframe when I'm analyzing its own bare capabilities. So I have assigned the mass. Once again, for my last and final ESC, so going to go ahead, use the query tool, search, and I'll be able to find the CG locations. I made a note of that. Next, I'm going to go create a node at that same CG location where I'd like to apply the point mass. So I apply the point mass here. And I'm just giving the coordinates for this node, same as the CG location. Now I have created that. It's just showing me a log that I've created that. Upon hiding it, now I can go ahead and create a discrete tie once again. So just putting it in the same group, going to go ahead, create a discrete tie, select that once again. And now once again, I can assign the mass properties for this in the form of a concentrated mass. So once again, going into attribution, applying a concentrated mass over here. As simple as that. So the mass of that property has been given. Again, like I mentioned, you can also provide the mass moment of inertia. It's a good idea to put the mass moment of inertia. So moving ahead, we then go into the motor weight assignment also. So like we saw, there are some regions. So first, we'd like to go and investigate the battery as well. So I know the CG location for the battery. Okay, that I've made a note of that in my notepad once again. So using the CG location of the battery, I'm not going to represent the battery in this analysis. I'm not meshing it. I don't have any data on the stiffness of the or the construction of the battery. So therefore, I'm only representing it as an applied mass in this. So going to go ahead, select the CG location. Once again, applying the CG location for a single node. I have created a node, and then I'm going to just move this node and point into the battery part. And then just going to repeat the same process of assigning a tie. So this is going to be an RBE3 connector. That is a compliant tie. And then go ahead, click on OK. And here I'm going to go ahead and assign the mass in this region again. So I'm going to have a point mass. This mass, I have evaluated it. So this analysis is in millimeter ton second Newton Kelvin. So I'm using the same unit system. You also have the ability of changing the unit system to SI. You can change it to any imperial units, whatever you like, all within Apex itself. So what I have done is I have taken the motors and I've also taken the propellers. And the motors are of a particular mass, and the motors have a CG point in that in the corresponding CG of the motor. And addition to this, you also have the CG of the propeller itself. So what I've done is I've just used a simple weighted average method of getting the net resultant CG, something very standard, what you've already done in strength of materials or even mechanics in your initial first year courses. So I just go ahead, take the CG location. I know that it's only going to change in the z-axis. So I take the CG locations individually. I take the mass of each propeller as well as the mass of each motor. And then using the cumulative mass and the cumulative weighted average approach, that's basically the weight times the arm, which is going to be the height of the CG. And then I multiply that, divide that by the summation of the weight, and I'll be able to get the resultant CG. So I apply a resultant CG point. So wherever these points are for the resultant CG of this structure, I'm going to go ahead and assign the points for these. So wherever those CG points are, I'm going to assign them. So you can see here, I've got that CG point, assigning that. I've created a node over there. Simply going to hide this. And then you can see the regions where this is mounted. I know where the motor is mounting. So this is where your motor mount, whatever connector that you're going to be using. So some fastener points for your motor mount. You can see there, there are basically 3 holes over there. So that is where I'm going to connect this. So I'm going to go once again, put these 2 points into the motors part, which not mandatory, but I like to keep all of my corresponding components in the same part. So I'm going to choose these holes where it's going to be mounted. That's where the load path is going to go. So it's also important to understand the load path and how it's going to go, but that is something that you would get by some experience, and you can also communicate with those who have had some experience in this as well. So once again, I know the cumulative mass of this. I'm going to apply that in tons. So I've applied that in tons. So it's 8.3 to 10 power minus 5 tons. And go ahead and assign the mass at that location. So you can also assign the corresponding moment of inertia, mass moment of inertia. For this case, I have not done that, being a basic analysis, but you also have the ability of assigning the mass moment of inertia. How do you evaluate the mass moment of inertia? Normally, CAD tools have a way of extracting that as well. And you can also extract the mass properties based on the material application that you have assigned. So it's not a very difficult process of doing that. So just going to repeat the same process for the other 3 motors as well. So we're going to go ahead, create a node, and then going to go ahead and assign a discrete tie for these as well. So you can see that, yes, I'm selecting the same holes for this motor as well, and then going to go ahead. And on that single individual point that's created, I'm going to create the lump mass parameter. And the mass has been assigned now. So very similarly, going to be creating this for the other 2 motors as well. So please do bear with me for this. So going to go ahead. I know I go to the query tool. I want to find what is my CG of this. The only thing that will vary is my ZCG. So I know the CG location, and then create a node corresponding to that CG location. Once again, take the cumulative CG location of the Z, and then I've created a node, so I hide the actual structure itself. So what you can see here is I don't really need to mesh components which are bought out, like motors, like ESCs, like controller boards or battery packs, things like that. All is what is my interest is what I have designed, which is my airframe. So it becomes a lot easier and a lot less tedious, and also computationally a lot more advantageous in order to do this. So one final motor is remaining. Going to just repeat the step for that. So going to go ahead, query tool, once again, investigate the mass properties. And it is going to give me the CG location for this motor. Going to take the cumulative CG in terms of the Z, because there is actually a propeller also incorporated. And very simply going to provide the values for the node that I'm creating and say OK, and hide the actual motor itself. And then go ahead, place these newly created points and nodes into my motor. And then very simply go ahead, create a link again, which is going to be my discrete tie, an RB3 element. Place that, yes, and then just go and apply the mass once again as a point mass over here. So now we are through with creating the masses for the motor as well as the battery pack. So next, we're going to go ahead and then create the same, which is going to be for a flight controller. So you'll have some kind of a Pixhawk or some flight controller that you have developed on your own, or some bought-out flight controller which you're going to assign. So the very same thing, I'm going to go ahead and I know the properties and the dimensions of my flight controller. So I'm going to take that. First, I'm going to find the CG location of this top whatever board that I have. I'm going to just quickly keep my calculator open, because the CG is going to be coming from my midpoint surface. I'm going to find the thickness of this. So it's 1.75 millimeters. So with that, I'm able to find the midpoint thickness, add that to the CG location of my choice, and I know that it's going to be 9 millimeters from the top surface. So I'm going to take that, and then I know where my CG location is going to be for my individual board based on the dimension of it. So it's just any generic board. So these are all just basic geometrical computation I'm doing. I'm just taking the CG of this board that's mounted on top of this. I'm going to say it's a flight controller board that's mounted. So utilizing this flight controller board and its corresponding location, I just assign a corresponding point over there. And I'm going to say that this entire board is basically mounted on this central board assembly. So once again, going to just use a discrete type. So you can see here, I'm not even modeling the flight controller board. That whatever component is there is not even necessary to be modeled. It is simply going to be distributed as a point load. I'm going to apply a mass at the CG and then allow it to distribute itself amongst the top surface of this structure. So please note, again, like I mentioned, you can also incorporate the mass moment of inertia. It is more appreciated to be present, especially when you're doing dynamic analysis. So please do go ahead, evaluate the mass moment of inertia. You can place the IXX, IYY, and so on and so forth. So once you're done, okay, now pretty much all of these have been assigned. We are able to look at this entire structure as it is. All the meshing has been done. All of the ties are created. All of the whatever the mass properties for the non-structural members have been assigned. And now we're going to create the material for the structural members. I'm just showing all of the important components which I'd like to look at for visualization. And next, I'm going to go ahead and create the material properties for this. So here you can see I have an easy way of creating the material properties and assigning them. We'll soon see what's going to happen. So I'm just showing you what is the structure looking like. So in fact, all of your complex geometry in terms of bought out components are all represented very simply by just point masses. So you have the option of creating materials. There are plenty of different kinds: isotropic, anisotropic, orthotropic. You have 2D, you have 3D, you have fluid elements, things like that. So for this, we're going to use a linear isotropic material. I'm going to call it aluminum. My frame is made of aluminum. You can well take different material properties also. So here I'm giving the density, Poisson's ratio, and Young's modulus, the three important things that are necessary. Next, I'm just going to call it as FR4. Of course, FR4 is orthotropic in nature, but for this, I'm just taking the isotropic equivalent property of FR4 for my PCB boards. So just assigning the FR4 properties in terms of Poisson's ratio, density, and the elastic modulus or Young's modulus. And I can create a corresponding property for this, which is going to be my solid property. I also have a way of creating a shell property, should that be a necessity at any given analysis, but all of my components here are solids. So I'm going to choose the solid property aluminum, and I can assign it to either parts, solids, or cells. And I'm going to choose solid bodies, and as I wish to assign it one by one, I begin to assign aluminum. So I'm just saying my entire frame is aluminum, and that's my base, that's my top, and then my spacers are also aluminum. So I choose these 4 spacers as well. Need to be careful not to assign it to the boards because they are PCB boards. So only the spacers are aluminum. Now the material application is completed. So just like that, I can assign the material. Next, I once again create the 3D element property, choose FR4, which would be my PCB properties. I choose PCB as FR4. Once again, I assign it. Here I take care only to assign it to my top and bottom PCB boards that I have placed in my mount, nowhere else. So this is done now, and my material is assigned. Next, I would start to assign the loads and boundary conditions. This is what become important. So you have your displacement constraint and you have your loading. So first, I would like to look at this analysis as if this is sitting on the ground. That is my base, wherever it is landing, these skids are placed firmly on the ground. So I'm going to give a fixed boundary condition. You have plenty of different boundary conditions. You have a manually assignable boundary condition, you have symmetric, you have spherical joint, You also have a sliding kind and so on and so forth. So here I'm just mounting the 4 points which are going to be. So first analysis is standalone analysis of this structure on the ground. It is not flying right now. Okay, it is sitting on the ground. No other loading. So the only force that's coming is going to be self-weight. So before we get into that, I'm going to create contacts. So as you know that all of these components are dissimilar in nature, the meshes are not mapped, so they all need to be held together. So all I need to do is just drag a box around them, provide a pair detection tolerance, and you can see that I have now created the necessary contacts for this. So like I mentioned, I'm not going to be creating any kind of a fastener. Instead of a fastener, I'm going to be using these kind of interactions which are in the form of contacts. And you can see all of these contacts are defined here. So you'll see the 4 arms where the motors are going to be mounted. And then you can see the landing gears which are going to be connected to that, the pegs. And then this is the arms connected to the top surface and then the bottom plate. And then correspondingly, you'll even see the mounting of the central control board assembly also. So like so, we in fact do not need to model fasteners. We can simply create joints or we can create contacts. So these are called glue contacts. So we have applied glue contacts over here to assign a contact constraint. And with that, you'll be able to see the regions where all the contacts are present. This will allow you to investigate the regions of contacts if they're appropriate. If they are not appropriate, you can feel free to individually manipulate each of these contact pairs also. So if you wish to choose anything and then study individually and then modify these, manipulate these, it is something that you can easily do as well. So with that, the next step is going to be the load assignment. So I'm just going to say show all. So just going to display everything. These are the RBE connectors that we have created, those connectors for the lump masses. Now we have the entire structure that's visible, whatever is essential for us. And then the corresponding point masses are also visible. Just going to be toggling the visibility to make it easier for everybody. And there you have it. So next, what is the next thing that we're going to do? So we have the mass, we have the boundary condition applied. We need to apply a loading condition. So a load condition becomes important to us. And here you can see how do we go ahead and create a scenario. So we need to create a scenario. And basically what we do is by creating a scenario, so we go to studies and we have different kinds of scenarios that we can create. And basically just going to I think this is just something that was a visualization. It has got highlighted and it was something to do with the graphics in my PC. So I'm just wondering how to eliminate that, but it's not something that's going to be essential. So there you can see all of the constraints that have been defined. And the next step would be to actually go ahead and see what kind of a study that we can create. So by default, you can see that the study created is a static scenario. You also have the option of choosing different scenarios. For now, I'm going to create a linear static analysis. And then I'm going to create a gravity load. So I want it to be in the Z direction. Magnitude is going to be 1g. That's 9.81 meters per second square. So this is going to be just sitting on the ground. I want to first study what's going to happen when it's sitting on the ground. So I choose the corresponding load and I choose the corresponding boundary conditions that I want. And I give a name. I'm going to call this as self-weight on ground. And then simulation settings, you can see all the solver controls, interaction controls, things like that. I'm keeping it default for now. No need to change anything. And then I have the option of requesting specific outputs. So I want stresses, I want applied loads, constraint reactions. I can also, by default, I will get my deformations and I can ask for strains also should I need it. Next, I will go ahead and place this in the analysis scene. So when I click place in analysis scene, it throws me warnings. Can you see the kind of warnings that are coming? It's saying some of the geometry are unmeshed. There are some empty models. There are some bad elements. So anytime you get a bad element, you get a warning. So these warnings are basically shown in yellow. Anytime you get a red warning, that means you can see here missing load. A red warning means that the analysis will not take place. You cannot proceed with that. And it will even show you what the problem is. So this basically gives you an ability of investigating and rectifying the analysis. So you can simply click on the yellow man on the bottom, or you can right click the analysis and say run, and the run is possible. So while this runs, we can just go ahead and see. So you can see that it's interactive in nature, and whenever something is not okay in your analysis, it even throws you a warning saying that this is the reason why it's not okay and what you can possibly do in order to correct it. So the analysis is also performed well within Apex, so you don't need to exit the environment. And the post-processing is also something that you can do in Apex itself. So right now the analysis is running. Maybe I'll just fast forward this for a few seconds. Yes, it is now almost complete. So in a few seconds, it will be complete. And there you have it. You have the completion of the analysis. So this, we would like to post-process this well within this environment. So by clicking that blue box on the right corner on the bottom, you're able to go into the post-processing environment. And here you're able to look at, of course, this is a model scaling. So you have true scale versus relative scale. You can keep it as true scale, or you can set the level of scaling you want. And you can probe where the stresses are maximum, where the displacements are maximum, where you'd like to change your design. You can clearly see that at the junction of that arm, where you have that that flange connecting, there is a stress concentration. And you also have a stress concentration where the motor mount merges with the rest of the structure. So such a capability is already there. You can also probe individual regions. So by using the probe option, you can go ahead, probe individual specific locations to see where you have high stress, where you'd like to change anything in your structure, any potential modification that you'd like to do. All of this can be seen. So you can look at the displacements as well. And this is on the ground, and you can also animate the displacement. So right now I've taken true. Now you'd like to look at the relative scaling, and just a small amount of scale I've applied. Since the loading is just self-weight, it will be very minimal. So you can see that the displacement is in like 10 power minus 4 millimeters. So very small. So you can actually see in true scaling, it's a tiny thing because this is just sitting on the ground with self-weight. Just wanted to see what's going to look like. In the next one, we'll see with some loading as well. So you can easily perform this. Next, we're going to take up the case where we're going to apply some loading to this. So that is, I wanted to see what's going to happen when this is actually flying. So I'm going to assign a specific thrust to this. So I'm saying each motor is having 50 newtons of thrust. Your motor may have any different value of thrust. This is rated based on your kV value and what is your operating RPM and so on and so forth. So you have an easy way of investigating that. And I'm going to just go ahead and create another node where I'm going to say the load is going to come from there. So I'm going to say that it is above the CG point by a certain value at the location where the propeller is going to be mounted. That is where my thrust is going to be generated from. So I go ahead, I calculate that. And then upon calculating this, I'm just simply going to apply this. So you can see here, once again, even for the load application, I don't need to do anything complex. I'm going to hide these points and these components. And wherever I've applied these masses, I'm going to simply translate those points because they're already at the CG. And I'm just saying that slightly above that is where I'm going to get my thrust from. That's where my propeller is mounted. And this may be different in your case, depending on whether you have a tractor type, you have a pusher type. So you may want to see where you're going to get your thrust from, a particular location. But I've made a engineering approximation that it is going to, in fact, be coming from the base of the propeller. That is where my thrust is going to be coming from. So you can see I'm just translating these notes, and I'm going to just translate them for all four of them. So you can see that similarly, I have translated for that one and that one as well. And you'll be able to see where it is sitting with respect to the propeller. So I'm going to hide the motor and the propeller again. Connect these using the RBE3 discrete ties once again. So just like what we did for the mass is also going to be distributed. So is the thrust. The thrust is a load, it's a force. So I'm going to be using these nodes and going to be connecting these nodes. So you can just select any one particular node, start with that, and then create discrete ties for them. So once again, just going to go into the points wherever they're assigned, and then going to create the discrete ties corresponding to these. So just want to move them to the motors. Like I mentioned, I like to keep them. So normally Apex puts all newly created geometry or FEA into the last part that we modified. So I just want to bring it back into my motors. So it's already there. And then I'm going to go into my discrete tie under interaction tools, choose the compliant option. So the same location where the mass is also mounted, that is where my force is also going to be mounted. So I'm just going to go and select the same region. That's where my thrust is going to come as well, but slightly above the CG. It's not directly at the CG. I'm assigning that point. So similarly for the other two motor locations as well, going to select the holes and then go ahead and assign that. Yes, that's done. And then for the final one, going to repeat the same process. Choose the mounting locations, and then choose the point at which the thrust is going to be defined. And finally, I'm just going to define a thrust. This thrust I'm going to say is vertically upwards in the positive Z direction. And the thrust value, like we discussed, is going to be 50 newtons in measurement. So according to my operating condition, I'm just assigning this as 50 newtons. You can go ahead and create different values also. And in fact, you can create different scenarios also. So I'm going to choose that node and I'm going to apply this as 50 newtons. And then the other one also as 50 newtons. So individually, all four of them are going to be 50 newtons. And once again, 50 newtons as well. So now you can see my four motors have the mass as well as the thrust assigned to this. Now, in studies, this is a very interesting thing. Clearly, now this is an airborne structure. It's not sitting on the ground anymore. You have gravity acting downwards, and you have the load acting upwards. So, like you see here, you have different conditions. You have static analysis, which we're going to do now. You can also do normal modes, frequency response, buckling, so on and so forth. So here, once again, I'm going to select all the loads. And can you see I have turned on something by the name of inertia relief. When inertia relief is selected, all of your boundary conditions that are your constraints are going to be removed. Because when it is airborne, it is not in a fixed condition. What inertia relief basically does is that it computes the internal and external forces and then finds a force balance between them rather than by finding a force balance by utilizing constrained options. So this is what is popularly done in the aerospace domain for larger aircrafts as well as UAVs. So we select inertia, the inertia relief option, and then we go ahead and perform the analysis. So in this case, we are having an airborne condition. You have the load applied and you have the thrust condition defined. And you have the self weight of the entire structure, which is basically the gravity load due to inertia. And we will be able to see what are the results looking like, what are the stresses looking like, is it going to fly appropriately or not. So this is basically a very, very basic first step approach to performing structural analysis of a UAV. That is the linear static analysis. You always do a linear static analysis before moving ahead into any other analysis. So linear static and normal modes is something that you would definitely look at. And then beyond that, you start to see more advanced analysis, like what happens about crash and dynamics. You want to see any kind of impact. You want to see any kind of frequency response, so on and so forth. All of those can be done. And that is something we are capable of doing at Hexagon as well. So the analysis has run now. We're looking at the results. And in the results, during the post-processing, you will be able to see the previous analysis as well as the new analysis. I'm just going to turn off this previous analysis. So I'm going to keep this latest analysis which we performed. Once again, the scaling will always be scaled. So you can see true scale when it's toggled. This is the actual deformation that you're looking at. And you'll be able to see the value of your translation deformation and also the stresses incurred. The stress is not too much. You're getting about like 35.9 MPa in a von Mises stress. So this is okay. So your loading condition is absolutely okay for your application need. So of course you can take this later on downstream into fatigue, and then you can take it into any other kind of advanced analysis, so on and so forth. You can use Apex as a pre-processor also to create the mesh and then utilize it for any more advanced simulation and so on and so forth. This is an animation of what it looks like. You have the mass actually acting downwards, and you have the thrust from your four motors pulling the frame upwards. And this is just a scaled view of it. That's it. And as you can see, we have actually done this entire analysis without the use of any complex structure which was unwanted for us in terms of the actual bought out item itself. So with that, I'd like to just take a pause for a moment. And what I will do is I'm going to stop sharing my screen and turn on my camera once again so that I can say hello to all of you as well. And with that, I would like to have about 10 minutes of question answers. And then I'd also like to share you some links where you can go ahead, download Apex, and then get started. So with that, firstly, I hope this was helpful for all of you. And please do share your questions. And do you think this would be useful for you in the future? And yeah, you can either put the questions in the chat where Aisha can read it out, or you can directly turn on your mic and ask me as well. So depending on how Aisha would recommend. So is that okay? Can we have the mics on?
Yes, sir. Students, you can unmute yourself and then you can ask your questions.
Yes, please. Questions, comments, any kind of use case you want to do, any kind of challenge you see, whatever you want, anything on your mind. Even if you found it not very useful, please share it also. If you think that is redundant for you or something that we can definitely check. So please do share your thoughts. Okay, how complicated? So Mr. Anthony Paul has asked how complicated. Let me just read it from the chat. How complicated will it be if we were to do dynamic analysis? That's a great question. So the workflow process would be the same. You would create the model the same way. You would mesh the model the same way. You would assign the mass, the material, everything the same way. Like I mentioned, you would use the mass moment of inertia also, not only the point masses. So definitely the workflow would be the same. Where you would have a difference is the load application, because you're performing a frequency response analysis, and you're basically going to be looking at a certain number of, so it involves the theory of dynamics. So if you're performing a frequency response, or if you're performing a transient analysis, you need to know the loading that you would like to give as an input. Are you doing a base excitation? Are you doing any kind of frequency loading as a pressure value? Things like that. So those kind of things are where you would have a difference in terms of what you're looking at. But the interface is one and the same. It's only the last step where you select the kind of analysis, and then you perform the analysis correspondingly to that. So it's not very complex. You do have examples in Apex itself to perform dynamic analysis also. And in the end of this, I will share my email address as well. So please do write to me if you want to do anything more advanced in this. And then if you get stuck somewhere, also write to me. I'll be able to help you out and so on and so forth. So hope that helps, Mr. Anthony Paul. So there is Mr. Nakul Kaushik has asked me a question. How is this different from a third-party FEA solver like ANSYS? That's a good question. My role here as a representative of Hexagon is not to be commenting about third-party FEA solvers. Where it does come into the picture is the ease of use. So maybe I can, you can try it out, explore it. And as you see, what I did mention is that if you were to make any geometry changes in your structure, if you were to remesh something, so I can once again go ahead and share my screen. So let me just go ahead and show that. So if you were to see any operations like you can see here, on your right top corner, you're actually making a manipulation in your geometry. It is automatically getting remeshed. And another thing is that you don't need to exit Apex in order to perform any kind of a analysis. So all of your geometry manipulation along with your meshing is automatically generated. And you can basically what I would like to say is that try it out, test it, and then see, maybe you can come back and tell me how different or how different it's not with comparison. The mathematics of it is all finite element analysis, but you can come back and see what's going to happen. Advantages and disadvantages of Apex over ANSYS. I would say use it, try it, and then come back to me. So this is by Ms. Rupa. And the question is, what are the advantages and disadvantages of Apex over ANSYS? They all have their merits. They all have their demerits. What I can do is talk about Apex. Like I mentioned, it has auto-generative models where you can manipulate the geometry without having to remesh your structure. You can export this mesh to be solved in MSC Nastran, and you have generally a lot easier way of approaching in terms of the user interface. So again, like I mentioned, that is something that I would urge you to try and use from the student community, and then make a decision based on how you feel it. It also has a lot of inbuilt tutorials and inbuilt videos, something that you can utilize that. And please do check that. Okay, Nakul has another question. So difference between normal mode analysis and frequency response. That's an excellent question. So normal modes analysis, you don't have any excitation load and you don't have any damping. So when you take a generic vibration equation, mx double dot plus cx dot plus kx equal to f, when you remove that c term and when you remove that f term, so you'll be left with mx double dot plus kx equal to 0, and you solve that analysis as an eigenvalue term. So you transform it into the matrix. So you say x is equal to your e power I omega. You can consider it as a e I omega as a modal domain. When you transform it to that domain, you're basically going to be solving an eigenvalue problem. When you solve an eigenvalue problem, you are going to get what is known as the natural frequency of your structure. So, for example, I have this pen, or all of you in high school would have done this physics experiment called you have a tuning fork. You strike the tuning fork, keep it near your ear, and it has a signature sound of its own. That is called a natural frequency. So normal mode analysis gives you what are the natural frequencies of a structure. What is frequency response? Frequency response is when you bring that f term into it. You excite this structure. So mx double dot plus cx dot plus kx equal to f, and then you excite this with that f. And that f is not only a constant, it is a f of t. It is a function of frequency and time. So when you go ahead and then perform this analysis, you are able to go ahead and see what is the effect of a excitation load at a frequency. So if you match the natural frequency that you get from a normal modes analysis, you are basically able to see a great level of amplitude increase, and you're going to have damage if you don't have a sufficient amount of damping. So that is the difference between normal modes and frequency response. How I hope that answers that question. So Sukrit has a question. What would you like to advise us as far as your experience goes on macro scale? So maybe, Sukrit, I'd like to ask this. I'm not familiar with what is this question. So can you clarify this? What do you mean by macro scale? Or maybe if you can just ask, you can feel free to turn on the mic and talk to me also. This is not a one-directional discussion. We are all students here. We're all aerospace engineers here. So don't worry about it. We're all engineers basically. So it's okay. So maybe I'll come back to that. So Sukrit, if you feel free to turn on the mic and ask that question again, we can discuss. Abhishek has a question. What is the difference between linear and nonlinear? Great question. Linear analysis is an engineering assumption that we make. We make three assumptions in this. One is that your material is linear and isotropic. That is, your stress strain curve has a linear parameter. You have not reached yield. You have not exceeded yield. It is linear and isotropic. If you remove the load, your structure comes back to the original shape. That is point number one. Point number two, your loads, whatever you have applied, is not rendering your structure to have any large deformations. They are all small deformation theory. You do not have large deformations here. Number three, you do not have any non-linearity in terms of contacts, such as frictional contacts, such as slips, such as any kind of detachment, reattachment of contacts, so on and so forth. So this is the difference between linear and non-linear. To be honest, every single engineering occurrence, whatever you see in nature, anything you see is a non-linear phenomenon, always. However, solving a nonlinear problem is mathematically complex as well as computationally very advanced. So when the difference between nonlinear and linear becomes less, that is, your loading is small, your material has not yielded, you're not having any kind of crazy contact conditions, everything is fixed for you right now. All of those come under what is known as linear. So linear is what you can use to perform. In certain cases where you have made an appropriate engineering approximation. So about 90% of our analysis that we do in engineering is normally in the linear domain. About 10% come into the non-linear. Of course, it's growing rapidly thanks to digital computing also rising in its capabilities every day. So hope that helps. Uh, okay, next, again, Abhishek has asked, what is the difference between static and dynamic? Very simple. Static means load is not varying with respect to time. Dynamic means load is varying with respect to time or frequency. That is all. So whenever you have a load that is varying with respect to time or frequency, you need to use a dynamic analysis approach. Okay. Will it take more time for processing? So Anthony Paul again has asked, will it take more time for processing for simulation if we reduce the size of the mesh? Yes, that is correct. It will. So where you make a decision is that you do something known as a design study or a convergence study. So you take a particular mesh, you start with that analysis, you record the maximum stresses, you record the location of the stress, maximum displacement, location of the maximum displacement, and then you begin to vary the size of the mesh. As you vary the size of the mesh, you will eventually reach a stage where the change of your stress and displacement values are not going to change with respect to maybe 5 to 10%, depending on what your convergence condition is going to be. And at that moment, you can say that you are getting a mesh independent solution, or you have a converged result. At that point, any increase in the mesh is going to only waste your computational resource. So you can stop at that point and say, this is appropriate for us. So I hope that answers your question. Okay. Okay. So we have, again, Sony asking a question. Is there any other advantage to defeaturing non-load bearing members apart from ease of simulation? Okay, good question. What is the advantage of this? One is that your simulation, if your non-load bearing component is, as I mentioned, it's not bearing a load, there is absolutely no use for modeling it. So you are going to reduce the number of elements used as well. So your computational time is going to reduce, computational effort is going to reduce. That is one. Again, if your non-load bearing member is very complex, and if you look at a ESC component or something, you have some sleeves in the end with some cables connected and things like that. Those cables are actually like made, you have a plastic jacket, which is highly nonlinear in nature. So modeling the behavior of cables, creating the material characteristics for them, modeling rubber and all that, it's no longer in the linear regime. You need to start using more advanced approaches for that. I'm basically reducing the complexity of the analysis because the presence of these non-load bearing members have no use for us. Okay. Now, second thing is there is a question on including fasteners in the analysis. How would it change the process flow? Not too significant, because what I'm saying now is that at my given conditions, so I have a top plate and a bottom plate. I have fastened this using some bolt, and there is a nut at the bottom. I've tightened it sufficiently, so this is going to be permanently fixed. I'm not investigating the characteristics of this mechanism of bonding. I'm saying that the top and bottom surface are completely mounted. So the presence or absence of a particular fastener as a three-dimensional model is irrelevant over here. However, there may be a case where you specifically want to model a fastener. That case is also present in Apex also, as well as other, like even Nastran has the capability of doing that. Again, something that MSC offers as a part of Hexagon. So in both of these tools, you have an ability of modeling a bolt. So you basically use a 1D element for this, like a bar element, and then you define the properties of the bolt to this. you actually have bolt elements that you can create, and you can select the centroid of the top hole, centroid of the bottom hole, and then have that bolt also modeled to behave like a fastener. Okay, so I believe I was still waiting. So maybe Sukrit, if you'd still like to ask that question, you're welcome to. I'm still unaware of what you mean by macro scale, but please do ask it again. Okay, all right. Then I have Wesley asking me, is it necessary to feature fasteners during simulation, or does surface contact make it enough? What is the difference it makes? Great question. Most often depends on the kind of mounting condition that you have. What we're saying is that these fasteners are already preloaded and they're bonded. And especially when you have a number of fasteners, that is like a row of fasteners or something that is mounting one plate to another, then in fact, you do not need to model fasteners. There are many cases where surface to surface contact is sufficient. So where you do need to model fasteners would come into the condition where you're investigating a bolted joint specifically, or you're investigating a kind of a riveted joint specifically. You want to see what is happening when the joint itself gives way and things like that. So most often, especially when you're dealing with a linear analysis or most of your approaches, I would say that a surface-to-surface contact is sufficient. But if you're trying to do any kind of nonlinearity where you define the frictional contact between these two surfaces, where it's called a touching contact, it's not bonded permanently, you have a coefficient of friction, and whatever is holding is the bolt pretension and things like that. You want to study the joint itself specifically. That's where a fastener comes into picture, and a fastener modeling becomes essential. Okay, great question, Anthony Paul. Apex, is it an open source software? No, it is not an open source software. You need a license. It is a very robust tool that you can use. However, it is open source for students. So what I am going to do is I am going to share you two links. So please do. I'm going to drop this in the chat right now, and please do tell me if you're able to get it. So I've shared one chat over here, one link in the chat, and I also have a student curriculum kit. So we encourage students to use. It's free for students, and all right. So you're able to go ahead and see. So you have this. Please open this link and see if it's accessible. Are the links working for you? So you can register and you can download Apex, the student edition. It's free for you. Start using it. And then you also have tutorial resources in this curriculum kit. Okay, Abhinav asked a question. Yeah, sorry, please go ahead.
Great, he said one more.
Sorry, I'm not able to hear you, Miss Varshini.
He just said me to see. I did not say it.
Okay, I'm shut down again. Okay.
Shut down.
Okay, I believe that is. I'm just going to request them to be muted. Okay.
Sir,
Yes, who is speaking,
Sir?
please?
Sir Karandeep, sir, I'm speaking. Sir, my question is about, sir, did we like if we have different material for defining like for the drone body, like how it would affect our like analysis, how we'll do it? And one more question, I didn't understand the 2D and the 3D meshing. I was not able to understand it.
Okay, no problem. I can explain both of these questions. So there are three questions right now. So Karandeep, I'll just come to you one moment. Abhinav has posted a question saying, what is frequency modes in modal analysis? So just to answer that question first, what modal analysis does is that it gives you the natural frequencies of your structure. So you have, for any continuous structure, you have infinite number of frequencies. It's unlike a discrete lump body. So this is something that you would be able to appreciate in mechanical vibration. So what modal analysis does is it gives you the natural frequencies at across the range of what you set. You may say the first 10 frequencies or the first 100 frequencies, or you can say frequencies between your 10 hertz to 1000 hertz or 100 hertz to 3000 hertz, depending on your analysis. And you'll be able to get the natural frequencies of the system or the structure in that itself. Okay, so that's what it means by getting the frequency. So we want to see at what frequencies, when these are matched, would actually result in structural amplification. That is something we're looking at. So yes, coming to Karandeep Singh, thank you for your question. So one question, okay, I will come back to you, Sukhrit, no problem. So Karandeep, you had a question. Can you please repeat your first question? I remember your second question about 2D and 3D.
So like if we have different materials, how will it affect our like, and it's like how will approach when we have different type of materials? Like for frame, like central component, I have different, and for the leg, I have different material.
Sure, sure. So like you saw even in the presentation that I was doing, I use the frame in aluminum, but you don't need to have every single component in aluminum. You would create a material of aluminum for certain parts. You would have composites applied for certain parts, maybe carbon reinforced polymers. You may have steel for where you have your high abrasion or kind of your landing equipment, whatever you have. So all you need to do is just create the material. What is important are to define the material properties, that is your Young's modulus and your Poisson's ratio and your mass, which is your density properties of it. You define this, and all you need to do is just assign it to that particular body or that particular part. So you're not limited in terms of applying material everywhere. You can apply it. All you have to do is, if you have a landing gear that's made of steel, put it as a different part or a different body, assign it specifically steel only to that, assign aluminum to wherever else you have aluminum, and I have assigned a PCB with FR4. So you can assign it differently, and it will react differently in terms of stiffness as well. When you're looking at the post-processed results, you may also have different strength criteria. Your ultimate tensile strength of steel is different from that of aluminum, which would be different to that of maybe some other material that you're using. So based on that, you may also have a different failure limit for that particular part. So that is where the difference would come. Definitely, the stiffer your structure is, the more the stress you'll experience, the lesser the displacement you'll experience. So depending on how you'd like your structure to behave, you can apply different materials and see the behavior. You're not limited to only one material. Hope that answers question number one.
Yes.
Okay. Question number two. What is the difference between 3D elements and 2D elements? So what I would urge you to do is take a look at a finite element analysis textbook also, but I will still explain what these are behaving as. So when it comes to a 3D element, so I'm just going to share my screen again. So just going to my presentation one more time. So if you see in my presentation, I have three kinds of elements which are specified over here. You can see that my bar elements or beam elements, these are all 1D elements, meaning all they require is just the cross-sectional properties and the length properties. These are used to define slender bodies. So you can see this is a communication tower, something like a telephone tower kind of a thing. So these are what are known as your 2D meshes or 2D element properties. What happens here is that essentially these do not have a thickness. Can you see? It is just a thin walled body. It is of zero thickness. So the structure has X and Y. You can say that X direction, Y direction, like it's like a plate essentially, and nothing in the Z direction. However, the Z direction thickness is specified by mathematically providing a thickness. So you can take a look at what is a Timoshenko element, what is a Timoshenko plate, and then what is a Mindlin element. So these are all finite element approaches. And these are approaches that are made for bodies which do not have a thickness which is very high in the Z direction. That is, it only has planar dimension, but the Z axis is very thin. So what I can say is I can assign that. So any kind of plane stress condition, those kind of conditions, or any kind of sheet stringer, like if you see a aircraft fuselage, it is a sheet stringer configuration. The sheet is basically the skin around it, and then you'll have your stiffness, and then you'll have your whatever your bulkheads are in the middle, those kind of things. So you can use a 2D shell element in order to create this. However, when you come into something like a 3D body, like you saw like a complex structure like an arm or something, and here you can see like a piston head, you roughly have equal dimensions in all degrees of all directions. So in such cases, you would apply a 3D kind of a meshing approach. And what I was showing in my example is that I'm using the 2D approach only to mesh a top surface to define what I want as a refinement and then mesh the entire thing as 3D. So my entire structure is meshed in 3D, not in 2D. So I will recommend you to read a little bit from a finite element analysis textbook. The book by Cook is good. There's an author by the name of Cook. And also, whatever is your prescribed textbook in your university as well for finite element analysis is a very good starting point. There's also a good book by the name of Practical Finite Element Analysis. I am not remembering the author, but that's a nice book to understand in terms of analysis side to apply less of theory, more of software application kind of an approach. So hope that gives you a idea, but definitely I would, you can always write to me also. I'll share my email at the end of this. Yes, I will suggest some books for you also. Definitely I will. Okay. Sukrit says, okay, unable to unmute, no problem. But like, what are the small problems that occur and few powerful tools that you have found in your experience? Okay, good question. Every tool is only powerful based on the way you use it. So depending on the problem that you have. For linear analysis, like you can see, Apex is extremely powerful, but it has limitations when you want to do any kind of nonlinear solutions. Although you can create a nonlinear deck, you cannot really analyze it in Apex. So you would bring it into something like Nastran, or you'd bring it into Ditran, depending on implicit nonlinear, explicit nonlinear, things like that. So you can go ahead and use it, and that is something that you can solve. So depending on your application, the kind of problem that you're solving, like you may want to do a bird strike, you may want to do a crash and impact, you may want to do some kind of nonlinear bending or whatever. So depending on the certification or your test and evaluation analysis of that, you would use the kind of tool that you have. So you can take a look at MSC Apex. You can just go to MSC software online, search what are the kind of tools that are there. They are superbly powerful. They have capabilities that you can do that. Yes, absolutely. So hope that helps you. Rajesh has asked, when do we use solvers like Nastran and not Apex? Excellent question. Apex pretty much is developed on a platform of MSC Nastran. It is interoperable with Nastran. You can export Apex PDF files into Nastran to solve. Nastran, however, has capabilities which are far beyond it. You can do aeroelasticity, nonlinear analysis, frequency response, direct as well as modal, transient response, direct as well as modal, explicit and implicit nonlinear, rotor dynamics, thermal analysis, and things like that. So that is where MSC Nastran becomes a solver. However, where does Apex become applicable in that case? Apex can be a preprocessor. You don't have to struggle in terms of meshing, applying boundary condition, giving contacts, constraints, loads, whatever. Just do your pre-processing, move it into MSC Nastran, perform the analysis in Nastran. That is something you can do, and hope that answers your question. Okay, basic specs needed to run the software. The resources that I have shared to download do have the basic requirements there. If it is not there, write me an email, I'll share it with you. So that's not a problem at all. Can you suggest some books for reference? Requesting you to write me an email, I'll send you a list of good books that you can refer to. But one of the good book that I can recommend is one by McNeil and Schwindler. So McNeil and Schwindler are the founders of MSC, and McNeil has written a book, Dr. McNeil. But also you can look at Cook to start with. That's also a book, finite element analysis. But I will send you a more thorough list if you just drop me an email with what kind of books with the same question over there. Is there any specific book for Apex? No, there is not. But with the links that I have shared, you actually have a curriculum toolkit where you have like tutorials and you have like the theory behind that as well. So it's like a hands-on tutorial. Please do take a look at that curriculum kit and read more. And Apex itself internally has a lot of videos, a lot of documentation inside. So you don't need to go externally. You can look at it inside. And Karandeep Singh asks, can we import a meshed file from Apex to ANSYS? Unfortunately, no. We work very interoperably within MSC software. So any MSC tool is able to communicate with Apex. That is, if you have like Mark, MSC Nastran, Ditran, so on and so forth. But when it comes to ANSYS, Apex does not have a means of communicating with that because yet, at least for now, maybe in the future it may be possible. I'm not sure. We are normally an open tool platform. We communicate with others also, but Apex right now doesn't have that. I will be sharing my email. Okay, please do write to me with your questions, and definitely would love to reach out to you. I would love to see you guys using this, and hopefully for SAE AeroTHON also, because you do have a manuscript that you need to submit for evaluation for your technical capabilities in terms of design, and you need to prove that. So definitely simulation is one means that you can prove. Instead of flying your quadcopter or multicopter and then saying that it's surviving XYZ, you can actually go ahead and simulate and also prove that I am able to reach the extent that simulation is proving what's happening. Instead of prototyping every time, you'll be able to save, and you can also check out different configurations. You may want to make it lighter, you may want to make it different, so on and so forth. So yeah, hope this was helpful. And any more questions? Okay, so if there are no more questions, please do write me an email with the request for books. So I'll know who to respond to. And maybe what I can also do is I can write a mail to Aisha and then have her share that to all of you with the books that are applicable. So hope that works. Aisha, can we do that? Is that possible? Okay, I will check with her offline. That's not a problem. But yes, so thank you very much, everybody. And I know it's a Saturday, but thanks for spending some time. What are the various types of analysis required for a quadcopter? Good question. Depends on what you're trying to do with it. So if you're trying to get it type certified, you have a QCI requirement when it comes to type certification. You can do n number of simulations. So you may want to look at the aerodynamic capabilities of it. You would use CFD to look at the performance of that. You would use structural analysis for, like, you may want to do static to understand what's happening as a first cut result. Then you would do normal modes analysis to see what modes of oscillation or what frequencies is going to be like critical for this structure itself. And then next, you would actually go ahead and see what are your frequency responses. You may want to see how the frequency of any excitation based on the uh, oscillating or rotating propellers itself is going to induce to you. You may want to look at bird strike. That is where you have a particular component coming in, striking like a bird hitting your craft. You may want to look at hard landing. That is also a simulation that you use. Even in QCI document, you have a basic requirement that during a landing or during any operating condition, even in a hard landing, you must not exceed a certain amount of energy. I believe it is 95 kilojoules or something, if I'm not wrong. So you're not supposed to exceed that. So if you have any kind of recovery mechanisms that you're trying to simulate, you may want to do that in the form of a crash simulation. And next, you may want to look at vibration analysis, that is base excitation. You may want to look at any kind of bump that could be like again a hard landing but transient in nature. And then you may want to look at fatigue. So fatigue is also something that you can look at. So you would utilize a platform to investigate cyclic loading. And then you can also evaluate your material. So you can perform material analysis. That is, if you have a composite, you want to evaluate what are its properties. So that is also something we can do using a platform known as Digiman in the Hexagon itself. So there are many kinds of simulation. The whole objective of simulation is to simulate reality so that you can match the physics that are actually occurring. So as an engineer, it's very important to understand the physics that are occurring on your structure or your aircraft, rather than try to simply do simulation for the sake of it, because you will get some result, but is it appropriate or not becomes very important. So always draw your free body diagrams, do some hand calculation, have some understanding as to what is the critical analysis that you'd like to perform. And then based on that, always take up the appropriate simulation. And you can always reach out to people like me or my team to see what would be the appropriate approach to go about this. And tools are a very small aspect. They just help the engineer to achieve what they do. It's the vision and the understanding that defines what analysis type is required. So hope that helps, Mr. Roy. Yeah. So if there are no more questions, maybe I'd like Aisha to give a conclusion on this. So Aisha, can you hear me?
Yes, sir, I can hear you.
Yeah, so maybe I'll just give it another minute or two for questions. And yeah, if there are no more questions, I'd definitely like to thank you all for taking the time on a weekend, despite your busy study schedules. And hope to see you again. This is just a start of a series of things that we'd like to talk about with regards to quadcopters. Hope this was helpful for all of you, and hope we can do this again in the future for more topics. So thank you very much from my end. Thank you, Aisha, for organizing this from SAE. It's an honor to be able to present to students as well as members of SAE. And yes, over to you, Aisha, for a conclusive remark.
Thank you so much, sir. Thank you for sharing your knowledge. And students, if you have any queries, you can drop the mail to marketing@saeindia.org. So we will communicate to Varun. Thank you so much, sir.
Yeah, thank you very much. Thank you, everyone. And no problem. You can all call me Varun. You don't need to address me as sir. So that's absolutely fine. All right. Thank you. Thank you, everyone. Hope this was helpful.
sir.
And
Yes, sir.
thank you. Eager to meet all of you again for our follow-up sessions on more topics. So thank you.